Hi everyone, this is second video for day 2, week 4. So we have been looking at trigonometric ratios. We started off by defining them for a right triangle, and then we went on to looking at it on a circle by constructing these different right triangles and observing that they change value from being positive to negative and so on. So they can be positive and negative. One of the analysis you did in week 3 was restricted to quadrant 1. We looked at values of sine and cosine. So we saw sine increases from 0 to 1, cosine decreases from 1 to 0. Now, forget about the values. If you look at the sign, that's confusing, the sign as in plus or minus. If you look at, let's say, the ratio sine, yeah, quadrant 1 it's positive, quadrant 2 it's positive, quadrant 3 it is negative, and quadrant 4 it's negative. Cosine is positive in quadrant 1 and then negative in quadrant 2 and positive. So they have this property where I'm going to go straight here to the graph where they behave somewhat like that. They increase, so this is sine. They increase in quadrant 1 and 2, so this is 0 degrees, this is 180 degrees. Quadrant 3 and 4, they are negative, 360 degrees. And you can find at these key values, like sine 0 is 0, sine of 180 is 0, sine of 360 is 0. But at this midpoint values, like 90 degrees and 270 degrees, sine of 90 is positive 1 and sine of 270 is negative 1. So they cycle along the same values, and the reason why they cycle is because they are generated by this point P moving around the circle. So they have the same values which differ by being positive or negative. Now, one of the applications is alternating current or alternating voltage. The background is, at the beginning when we really started producing electricity, there was only DC source. For example, you have batteries. What this means is, if you plot a graph for time and say the voltage offered by your source, then it's just a straight line. This is a constant voltage. Now that's one way to supply power, right? That's what we use in our phones. Anywhere you have batteries, those are DC source, which means once you connect the device to the source, it just provides a constant voltage. The voltage causes current to flow and everything works. But when it comes to transmitting power over long distances, from power plants to your houses, this is not a very good method because there's a lot of loss involved. So instead, what is done is from the power plants is our supply is an AC voltage. So over time, the voltage goes from being positive to negative. Now, the negative voltage doesn't mean that it's driving power from you. It's just a way of transmitting power so that the terminals change their polarity from positive to negative. And that's why all our main supply are going to be in AC, and our phones or laptops are powered by DC. So we use an adapter which changes this AC into DC. So these adapters are basically a bunch of filters that sort of chop down the AC to give you a constant DC voltage. Now, because sine theta, or the sine, it goes from 0 to 1 and negative 1 to 0, the max value that it can take is positive 1 and the minimum value it can take is negative 1. So that gives us an equation for the voltage. It's called E equals E max sine theta in the most simple form. Now, what are these things? Emax is called the maximum voltage. For example, in US, this supply is 110 volt. And the small e is instantaneous voltage, which means at the moment what is the voltage. So if your supply is 110, because you're multiplying by sine theta, it's not going to be always 110, right? It's going to be 110 here, it's going to be a negative 110 here, and it's going to be anywhere between 110 and negative 110 at any other given point of time. Okay. Now for all mains supply, there is also another feature called frequency, which we are going to talk about soon. Here's an example. So it says, what is the instantaneous voltage of an alternating EMF, which is, EMF just means electromotive force, which is voltage or a power source, when it has reached 160 degree of the cycle. The max voltage is 600, round to the nearest tenth. So it's very simply asking you what is small e when this Emax is 600 and your angle is 160 degrees. So you plug all of these numbers in. 600 times sine of 160 degrees gives you 205 point, says round to the nearest tenth, so 0.2 volts. Okay, so at the 160 degree point of this particular voltage supply, somewhere here, 160, this value is 205.2 volts. Okay. Now, as I said, this cycle sort of goes on, right, linearly. It just repeats itself. So far we've said that, well, things end at 360. Not really end, but you reach the same place at 360. So the next question is, well, what happens as I go along this x-axis here further to the right? So that's the case when you are at an angle greater than 360 degrees. So for example, determining tangent of 472. Now what does 472 degree mean? It means I went one cycle, right? That's 360, and then I went further. So I need to determine how much further I went. How much further I went, I can determine by subtracting 360 from 472, which is 112 degrees, which means I went 90 and a little more. Right, so the little more that I went is 112 degrees. Now from our ASTC, I know this ends up in quadrant 2. So quadrant 2 is sine positive, so I expect tangent to be negative. So let's plug this into the calculator, and we know we're expecting a negative value, negative 2.475. Now, what about tan 112? We expect tan 112 to give us the same exact value, and it does, because tangent 112 takes you to this point, and tangent 472 takes you one full circle and back to this point. So they always have the same value. So which means when you're finding functions of angle greater than 360, you can remove multiples of 360, and whatever remains, the ratio or the value for that angle has to be the same, because it just repeats itself after 360 degrees. Okay. Now, as I said before, when we look at any main supply, there is a voltage rating and there's also a frequency rating. Right? You can look at your devices. The most common frequency ratings are 60 hertz or 50 hertz. So let's look at the one that's used in US. It's rated as 60 hertz. Hertz is just a unit for frequency. Unit for frequency. Right? For example, you may have seen it in like refresh rates for your screens. or your monitors, right? So what that means is that's how many times the screen is flickering or updating itself. So you can see video, because video is just a bunch of images one after the other, right? Just like old school animation, where they would take pictures and play the pictures fast enough so our eyes cannot detect the granularity of it, so it looks like it's moving. What 60 hertz means is it means there are 60 cycles per second, or there are 60 cycles in 1 second. Now each cycle, remember, each cycle is the voltage going up to the max, going to the min, coming back to 0, and each cycle is 360 degrees. So in 1 second, how many degrees does it cover? It covers, let's see, 60 cycles. So 60 times 360, which, let's see how much is that, is 21,600 degrees in 1 second. Or, no, that's a question mark here. What this means is the main supply, the electricity supply that we get, it cycles or it goes through 21,600 degrees every second, and that's what this frequency means. So the question, or what we did in the previous case, can be framed in a different way. Here we were trying to find the instantaneous voltage when we were given the angle is 160 degrees, but usually we measure duration not in angle but in time, so in seconds. So in this case it says there is a 60 hertz alternating EMF. What's the instantaneous voltage at the end of exactly 0.03 seconds, where Emax is 120 volt. So first of all, I need to go from these seconds to degrees. I know 1 second is 21,600 degrees, so 0.03 second is going to be 0.03 times 21,600, which is 648 degrees. So 648 degrees actually puts us at 1 cycle. 648 minus 360 is 288, and then somewhere here it puts me here. So E is E max sine theta, which is 120 sine of 648. Fourth quadrant, ASTC, so I expect it to be negative 180 sine 648, negative 114.13 volts, which means at 0.03 seconds the polarity is switched, and the voltage across our source is negative. Okay. Now this part, A and B, is similar to what I showed here, and part C is slightly different, where I'm trying to find the instantaneous voltage at 0.04 seconds, 600 volt supply, but it's a 50 hertz supply. So I'll show this one. 50 hertz supply means 50 cycles in 1 second, which means 50 times 360, 18,000 degrees in 1 second. So 0.04 second would be 0.04 times 18,000 times 0.04, 720 degrees. And that's a multiple of 360. What happens to sine in multiples of 360 or multiples of 180 is it becomes 0. So the instantaneous voltage here is actually going to be 0. And you can verify by plugging in 600 times sine of 720 is 0. Which means in the circular it goes around once and it's back at 0. And at the graph you are somewhere here after 0.04 seconds. Okay. I'm going to leave you to do A and B by yourself. There's also a problem related to this on the worksheet. That's it for